Welcome back, everyone. So let me just quickly go over what happened yesterday, and we will today we plan to cover new things, sort of more recent ideas. Last time we talked about some basic algorithms for caching. So let me just go back to the beginning. We talked about deterministic algorithms, randomized algorithms. One thing I didn't, of course, people ask, but we when we talk about randomization, we always talk about oblivious adversary. That is, the adversary is not able to see your random coin tosses. Otherwise, it's basically same as deterministic. Then we talked about deterministic algorithm, which is the LRU algorithm, and we showed that it is k competitive, right? Which means that the ratio is k. But then we sort of saw some ideas which said that if you allow randomization, then I can get like a log of k, right? So I kind of showed you some of these proofs, or essentially some ideas. And then towards the end, I mentioned some of the extensions. So two of these extensions, which are weighted paging and generalized paging or caching, these are sort of classical. They have been studied for last 20-25 years. And then I also mentioned some of the mild works, where we try to generalize it by these two directions, which were elastic caching, where your cache size can evolve over time, it can change over time. And then caching with delays, where each cache page request comes with a time window, where you say that I don't have to get it in that cache right now, but I can wait for a particular time window. So you can look at those references. But today what I want to do is I want to go back to the usual caching and talk a little bit about more modern techniques which have come up in the last 15 years or so.
So,
yeah.
So in the case of generalized caching, is there any relation between S and W?
Yeah, that's very good. So there are various models actually. Okay, so I don't know what the names of these models are. I kind of forget, but I'll mention that in a minute. So but what I want to say is that a lot of exciting techniques have come up in the last 10-15 years. I will only touch upon some very basic ones, but now there are connections with online learning. There are connections with other kind of techniques. So but what I will talk about is connection with linear programming, and this has been an exciting area of research or connection in the last 10-15 years. Okay, so yeah, coming back to your question, let me just quickly mention what are the basic models. The first one is, so I wrote these things down so that I don't have to, I can go a bit faster. So unweighted caching is where you are given a fixed cache of size k, and you have to minimize the number of evictions, right? Then we had this second problem, which was weighted caching. And now here thing was that each page P has a weight WP. And again, it's the same problem, but then you want to minimize the total sum of the weighted evictions. So in other words, if you evict a page P, you don't count that as one eviction, you count that as weight WP. And now you want to evict, minimize the total sum of weighted evictions. So in other words, if you're evicting a page which has very high weight, then you're paying a lot. So you don't want to evict a page which has very high weight. You want to evict pages which have low weight. Okay, and then we had this generalized caching problem where for every page P, there are two parameters, a weight parameter and a size parameter. Okay, and this cache has a size, let's say some size B here. And what you want is that, first of all, again, just like weighted paging, your objective function is to minimize the total weight of the evictions. But now the cache, instead of saying that it has a size or it can hold k pages, now you say that the set of pages that it holds, their total size cannot exceed B. Okay, and now there are various submodels. One submodel is that what if WP is equal to SP? This is the most it's a natural model where it's saying that think of WP or SP as the actual amount of memory occupied by this page. In which case, it contributes the same amount towards the cache size. And similarly about the eviction cost can also be thought of, how much time you're spending. So I kind of forget what this model is called, but yeah, this has been explored. The other model is where WPs are 1, but SPs are arbitrary, right? So now, in other words, you just count how many evictions are happening. You don't count, look at their weights, but then when talking about the cache size, you actually look at their sizes. Okay, so both these models are there. Okay, so they're all special cases of generalized caching. I should also say that generalized caching is NP hard because simply because you can think of like knapsack being a special case of this problem, right? So um, knapsack is, you're given a fixed bag B, and you pack a certain pack objects in it, and that already is NP hard. So generalized, it's not surprising that generalized caching is NP hard, whereas the other two, you could solve them in polynomial time. Okay, if the entire input was given to you. Of course, we are in the online setting, so anyway, this doesn't matter, but I guess it's worth noting. Okay, now what I want to do now is I want to relate caching problem to the set cover problem. Okay, now set cover problem is a very classical problem, and it has been studied a lot in literature. So let me remind you what the set cover problem is. Okay, set cover problem is the following: that you're given some elements. Okay, so think of some set U, and this is some sort of universe, and you're given some universe U, and you're given some subsets of this universe. Okay, so let's say this is some S1, you're given some S2, okay, some S3, okay, S4, S5, and so on. And what you want to do is you want to pick some of these, a sub collection of these subsets. Okay, so let's say you will pick maybe S1, you may pick S5, you may pick S7, and so on. And what you want is that these sets should cover the entire universe. So every point must be in at least one of these sets. Okay, so the union of the sets that you pick should be your ground set U. Okay. So and the objective is to minimize the size of this subcollection, how many sets you're picking. Okay, so this is called the set cover problem, and this is a standard one of the first problems that you will study if you study NP completeness, and it's known to be NP hard or NP complete, right? A slightly more general version of this problem is called set multi-cover. And what happens in set multi-cover is that it's exactly the same problem, okay? But I also specify sort of a parameter S here, okay? So you're also given a number S, and what I want is that for every element X in your ground set U, at least you should have picked at least S sets which contain it. Okay, so the usual set cover problem will correspond to the case when this S is equal to 1. Okay, because when S is equal to 1, you are saying that you want to pick a collection of subsets where every element is present in at least one of these sets. If S is equal to 2, you are saying that you want to pick a collection of subsets where every element is in at least 2 of these. Okay, so this is called a set multi-cover problem. Okay, so again, set cover is a special case of set multi-cover, but the kind of greedy algorithms that you may know for set cover, they also give the same guarantees in terms of approximation ratio, if you know what an approximation algorithm is for set multi-cover problem. But I will talk about set cover, but really it's set multi-cover which is of interest for us. Okay, so I hope both of these problems are clear. Okay. Good. So now what I want to do is I want to give you a reduction. Okay, I want to reduce. I want to go from caching, and let's start with the unweighted caching problem to begin with. Okay, so I want to start with unweighted caching, and I want to reduce it to the set multi-cover problem. Okay, I want to show that it can be thought of as an instance of the set multi-cover problem. Okay, that's what I want to do. So let's picture it like this. Okay, so let's say that so this is the picture. So for every page P, okay, so let's look at its timeline. Okay, so this is just telling you the timeline, and these crosses denote when this page P is accessed. Okay, so these are the times at which this page P is requested. Okay. And let me have a notation. Let me call TPJ as the time at which the page P is accessed for the jth time. Okay, so in particular, this will be, let's say, TP1, this will be TP2, and so on. Okay, so TPJ is just telling you the jth time at which this page is accessed for the jth time. Okay, similarly, if you look at some other page P prime, this will have some others, its own timeline, and again, you can define these points in time where this page is accessed, and you can number them as, again, 1, 2, 3, and so on. Okay, so I hope this definition TPJ is clear, right? So it's a time at which the jth page is accessed. The page P is accessed for the jth time. Okay, and let me just define IPJ as the interval between two consecutive such times. Okay, so IPJ is the interval between the j minus 1th access to P and jth access to P, and it is the open interval. Okay, so I'm going to sort of make some assumptions that all access times are at integers. Okay, or integral, doesn't matter, but you can make this. And of course, at any particular time, you only access one page. Okay, so this is just setting up the caching input. Okay, and now you can ask, okay, so if I am going to reduce it to set multi-cover, I have to tell you several things. I have to tell you what is the ground set U, what are the subsets I'm talking about, right, of the set U, and what is the parameter S here. Remember, S was telling me that how many sets should be covering each element. Okay, so I have to tell you all of these things. Okay, so let's do that. So the ground set U is just the set of all time slots. Okay, so all the integer times. Okay, T is like, capital T is like the last time. Okay. So we don't know capital T in the online setting, but let's think of this as an offline problem right now, so that we can understand the reduction. Okay. So this is your ground set. Now, what are my sets? My sets are essentially the time slots corresponding to each of these intervals. Okay, so so let's call these sets. I will call these sets as SP, J, where P is a page and J tells you the jth access to this page, and it's just telling you all the time slots in this. Okay, so basically, all the time slots in this interval. Okay, so SPJ is just telling you that. So for example, if IPJ is 2, 7, then SPJ will be 3, 4, 5, 6. These are the integer times in this interval. Okay, so far so good. So right, so the way to think of this is not that in this description of SP, J, the P goes away. There is no P there. Okay, so for example, if this time was 5 and this was 8, then this SP prime, J prime would be 6, 7. Okay, so these are the sets. Okay, so each subset is like just a sequence of a set of, in fact, just an interval of time slots. Okay, and what is my parameter S? So the way to think of this reduction is that there is a cache, right? This is a cache, and this is like the complement of the cache. Okay, and when I say that the cache can contain only up to k pages, what you're saying is the complement of the cache must have at least n minus k pages. Okay, and the complement of the cache is behaving like the set cover problem. Why? Because in the set cover problem, we are saying that every element must be covered by at least so many sets. Okay, so think of it like that, right? So we're really saying something about the complement of the cache here. Okay, so the parameter S would be n minus k. What are n and k? K is the size of the cache and n is the total number of pages. Okay, okay, so let's just check that this reduction makes sense. So let's take this picture here where you think of some time t. Okay, and suppose the cache can hold 2 pages. Okay, so cache is of size 2, which means that at any point of time there must be at least one page which is not in the cache, right? So if this is the complement of the cache, then at least one element must be there which is not in the cache. There could be several more than one pages which are not in the cache, but at least one page has to be outside the cache. Okay. Now, okay. So let's see. So these are the intervals. So I have marked these intervals. So this is, let's call this interval. Let's say this was the jth access to the j1th access to p1. So this is I p1 j1. This interval is I p2 j2. This interval is I p3 j3, and so on. Okay. And what I want to say is that if you look at any time t, so let's look at time t here. At this time, okay, so what's the meaning of picking a set here? Okay, so when I say that you have to pick a set sp comma j, what it means is that during this interval I p1 ip comma j, you should have evicted the page p. Okay, so remember this sp comma j corresponds to, there's a page p, and this is the jth access to the page p, and this is the j minus 1th access to the page p, and sp comma j corresponds to this interval, right? So intuitively, what I want to think is that if you are going to select this set S in your solution, sp comma j in your solution, it means that you are evicting this page p during this interval, at some point during this interval. Okay. Fine. Okay. So now if you think of, let's think of any time t. Okay. So think of any time t and just look at which intervals contain this time t. So for example, in this picture here, IP1 J1 contains T, IP2 J2 contains 3, IP3 J3 contains T. Okay. Now, out of these 3 pages, at least one page must be outside the cache, right? Because there are 3 pages and the cache can only hold 2 pages. Okay. So what that means is, one of these 3 pages must be out. Okay. So let's say P1 is out. Now, if P1 is out, we know that P1 was accessed at this time. Right, so P1 was accessed at this time. It was in the cache at this time. So that means that P1 must have been removed from the cache at some point during this time. Let's call this is T1 P1 J1 minus 1. So at some point during this time T to the current time T, right? So during T P1 and J1 minus 1 to T, at some point during this this interval, this page P1 must have been evicted, right? Because otherwise, it was in the cache at this time, it is not in the cache at time t, it means it has been removed from the cache. Okay, so this is what I would mean when I say that you must have chosen this set sp comma sp1 comma j1. Okay, so so now it says that, look, for every time t, this condition must hold, right? That if you look at all the intervals which contain this time t, out of those, at least n minus k pages must have been evicted during these intervals. Okay, and that's exactly the meaning of this set cover problem here. Okay, set multi-cover problem. Fine. So is it clear? Right. So if you give me a solution for the set multi-cover problem, that is, it is telling me which sets to pick, I can tell you exactly which pages to evict at which time. Why? Because if you are going to pick this set sp1 comma j1, what I'm going to do is that as soon as this interval ip1 comma j1 starts, right? So as soon as this interval ip1 comma j1 starts, I will at this beginning I will evict this page p1. Okay, because this set has been chosen by you, and because you have chosen this set, you have paid 1 unit for picking this set, and that's exactly the number of evictions that I will have. So the number of evictions will be equal to the number of sets that I pick. Okay, and if you have n minus k pages outside the cache, it means that you're only holding k pages in your cache, so that's fine. Okay, right. Similarly, if you have a caching solution for me, then whenever you evict a page, I will know which interval that page that time was present in, and I will pick that set sp comma j. Okay, so essentially the 2 instances, I mean, this is the reduction between the 2 problems.
May I just add one thing? Just clarification. So it's not necessary, right, that between 2 consecutive requests, like at J1 minus 1th point, J1, that page P1 had to be evicted. It's just that for this purpose, it doesn't matter because there will be some other n minus k.
So yeah, I mean, either P1 or P2 or P3, one of them must have been
evicted. Yeah, right. At least n minus k of them would have been evicted
during those intervals.
Yeah, that's the thing, right? Because P1 can still stay in the cache at that time.
Absolutely.
There will be other pages which must have been evicted.
Could be P1, could be P2, could be P3, but at least there must be at least one of these pages which were evicted. Because at time t I can only hold 2 pages, and the point is, if you look at these times here, when the pages are accessed, all 3 of them are in the cache at those respective times.
Correct.
And at time t I'm only having 2 of these, so one of them must have gone out. Okay, so that's why we are defining these intervals like these. Yeah, good, thanks. Okay, so and this is a set multi-cover because I just if suppose I had 4 pages, then I am going to say that at every time t at least 2 of these intervals must have been chosen, or 2 of these sets must have been chosen. Okay, so it really is a set multi-cover problem, not a set cover problem. Okay, now let me quickly say this was for the usual caching, but what happens to weighted caching? Well, it's the same problem, except that in my set cover I can make it more general by saying that every set has a weight associated with it. Okay, and instead of picking a minimum cardinality collection of subsets, you want to pick a minimum weight sub collection. So you want to pick a few of these sets, and their total weight is minimized. Okay, and then it's exactly capturing the weighted caching problem. What about generalized caching? Again, you can capture this now as before. The sets will have weight, and now and now what will happen is that sets will have weight and they will have sizes. And then instead of saying that at every time t, at least n minus k sets should be chosen containing time t, I should be saying that if you look at the sets that you have chosen which contain this time t, their total size should be at least the total size of all the pages minus b. Okay, so essentially the same kind of ideas will work whether you talk about weighted caching or generalized caching. The only thing is that the way you will generalize your set cover problem is that in the weighted caching you will say that every set has a page as a weight, and in the case of a generalized caching you will say that not only every set has a weight, but it also has a size. And then what we will say is that instead of this parameter s here, we will have some other parameter b prime, and we will say that for every element x, if you look at all these sets which are containing this element, their total size must be at least b prime. Okay, so all of these can be captured by suitably looking at the corresponding version of the set cover problem or the set multi-cover problem. Okay. So what we have done is we have just sort of thought of these as special cases of set cover problem. Okay. Or set multi-cover problem. Any questions here so far?
Amit, one quick question. This reduction, does this work in, let's say, a bi-criteria approximation setting where you are allowed to keep more than, let's say, 1 plus epsilon times k many pages in your cache?
Right.
Because this n minus k thing is a bit messed up, right? I mean,
no. So no. So this also works for h comma k caching. All you will say is that look, what's the size? How will this parameter change now? Sorry, this parameter will change by saying that instead of requiring, I mean, this is instead of requiring that you, of course, in the offline optimum you want n minus k, but in my solution I'll ensure that you only have like n minus h, where h is some number which is bigger than k. So essentially you will be giving a relaxed covering constraint. The algorithm will satisfy only a relaxed constraint, whereas for the offline optimum you will require n minus k. So in fact it will go through even for h comma k kind of paging.
I see. Thanks.
Yeah. Okay, good. So now now 2 questions remain, and these are 2 important questions. First of all, okay, this was the reduction. By reduction we mean that if I give the complete instance of set cover and I give the complete instance of paging, then I know how to map between the 2. But what happens in the online setting, right? So now you can again define an online version of set cover, right? So I can define what is called an online set cover or online multi-set cover in the following manner. And when you're thinking of online set cover, you should really think of this connection with paging. And what is the connection with paging? That you have these intervals and you have a time t, and at every time t you want that I have picked enough sets which contain time t, right? Okay, so so what's the definition of online set cover? We know the definition of online paging, and the way I'm going to define online set cover will exactly mimic our connection with online paging. Okay, so so we'll say that in an online set cover, so again, remember there are several things. There is a ground set U, and there are subsets S1, S2 up to Sn. So if you look at time t, I have only seen some of the elements. Okay, so elements are going to arrive at time t. Okay, so sigma 1 arrives at time 2. So you don't know exactly the set of all elements at time t. You only know up to sigma t. Okay, so there are some more elements which are sort of hidden right now, which you don't know. Okay, and so the same happens for sets. You suppose this is some sort of set here, then you only know the elements which are present in S1 which have arrived. Okay, so in some sense you only know the projection of these subsets to the elements which have arrived so far. Okay, so for example, let me just maybe make it more concrete. So suppose this is 1, 2, let's say 1, 2, 3 have arrived, and you have not seen 4 and 5 yet. And suppose S1 was some set like this, then as far as I know, S1 contains 1, 3 only. And when 4 arrives, I will see that S1 contains 4 also. Okay, fine. And this is consistent with our definition here, right? Because as time goes on, every element is a time for us. For us, the elements which have arrived till time t are going to be just the times 1, 2, 3 up to t. And till time t, I know everything. I know what are the sets till time t. Or in fact, if you look at SPJ or SP1, J1, I know that till time t, this is the set, the projection of the set on the elements which I've seen so far. Okay. And then, when an element sigma t arrives, you want to ensure that the set covering constraint for sigma t is satisfied. That is, if it's just a set cover problem, you want to ensure that you pick a set which contains sigma t in your solution. If it is a set multi-cover problem, you want to ensure that there are S sets which are covering sigma t in your solution, and so on. Okay. And once you pick a set, you cannot undo it, right? You cannot discard it later, because picking a set here means that you have evicted a page. So once you evict a page, you cannot go back and say that no, I want to change that. That cannot be done, right? So once you pick a set, that's it. You have to stick with it, right? So that's where this online thing comes in, that you cannot change your decision as time goes along. Okay.
Can I ask another question?
Yes.
So the elements arrive on an online fashion, right? But the identity of the sets, for example, what exactly S1 is, shouldn't I know the set the composition of the set, elements of the set S1 before I can actually see the system?
Right. So there are two models. One model is, there are two ways of thinking about it. One way of thinking about it is that, I completely reveal to you the set of all elements, right? And it's just that you don't know which elements have arrived. Right. So I give you the entire instance in advance. You know exactly what all the elements, what all the sets are, but initially all the elements are inactive in some sense, and as time goes on, some of these elements are going to arrive. And at any point of time, you just want to make sure that you pick enough sets to cover the elements which have arrived. So that's one way of thinking about it. The other way of thinking is that you just know the identity of the sets up to the elements which have arrived so far. Okay, so I tell you that these are the elements so far, and these are the sets so far. Each of these sets may contain more elements, but this is something you will only get to know later. Okay. Both ways of thinking are more or less equivalent, because if you don't know which elements have arrived, there's nothing you can do about them, right? You don't know which ones of them will arrive.
Right. In the first case, still has to be on time, right? Like as the request, that is when I have to make the decision irrevocable. That's even if I know the identities of the set, and I can't do anything about it.
You're absolutely right. Even if I told you the identity of the entire set of elements, you would not know exactly what to do. Yeah, you're right. It doesn't help you. Yeah, knowing the identity of all the elements doesn't help you till the element has arrived. Yeah, at least here. Yeah.
So Amit, are you defining this for the multi-cover version as well?
For the multi-cover.
So then my question is that is the demand revealed like all at once, or it can happen that at some point more demand for a specific element is added?
No. When an element arrives, this number S is fixed for us. Okay. So by the extent to which you want to cover an element, that is fixed. That's not going to change. It could change, but for us, let's say it is fixed. Okay, at least at least in our connection with paging, this n minus k is fixed, right?
So when this element arrives, you have to make sure at that very point S sets are there for that.
Yeah, covering this.
Okay.
Yeah, absolutely. I mean, that's the connection with paging, right? When this element arrives at any point in time t, you want to make sure that there are only k pages in the cache, right? That is, n minus k pages are outside the cache. Okay. And this has to be true at every time. Okay. And how are we capturing that? You're requesting a page, when a page request for a page arrives, why will that page be in your cache? Because it will be in your cache because, when I look at the constraint for this time t, there is no interval containing p2, right? So I'm saying that without counting p2, you must have n minus k outside. Okay. So that's how you can ensure that p2 is in the cache at that time. Okay. Because I don't have an interval containing p2 at this time. Okay. So whenever p2 is requested, p2 better be in the, I can bring p2 in the cache, because there will be an extra slot for p2 available, because even if I don't count p2, n minus k pages are outside. So that's how we are ensuring that you're able to service a page request. Okay, and we're only counting evictions. We're not counting the cost to bring in a page, because as I said last time, the two are the same. Okay, questions? Good. So this is the online set cover problem, and I want to sort of maintain a basically what you're doing is you're maintaining a collection of subsets over time, and once you pick a set, you cannot throw it away. Okay, and you want to, and what we are showing is that if you can solve this problem, then you can also go back and solve the paging problem. Okay, but the question is, how do you solve online set cover? Okay, and here, we need a richer set of techniques. We can't just go back and rely on simple ideas that we had last time. I mean, these algorithms are also simple, but you at least need some sort of conceptually new steps here. Okay, and the new conceptual step which we have here is called fractional set cover. So what I am going to do now is I'm going to sort of so let's go back to just the usual set cover. Okay, let's not worry about multi-cover and weighted sets having weights or sizes. All of those can be incorporated. But let's talk about the usual set cover problem. Okay, and instead of thinking of set cover where you're picking sets, what I'm going to do is I'm going to think of a slightly a different but a related problem, which is called a fractional set cover problem. Okay, and this is an idea which comes up a lot in approximation algorithms. If you have seen approximation algorithms, where instead of solving the integral version of a problem, you solve the fractional version of a problem. So what is a fractional set cover problem? In a fractional set cover problem, I say that you can pick a set S fractionally. Okay, so earlier I was saying that either you pick a set or you don't pick a set, but now I can say that the set S can be picked to a fractional extent. So that suppose, for example, you can pick a set to an extent of half or a third. Okay, what will it mean for us in the sense of paging? In the sense of paging, it would mean that if you pick a page to an extent of a third, it means that 1/3 of the page is outside and 2/3 of the page is inside the cache. Right? And which is kind of strange because we don't allow that, right? Either the whole page is in the cache or it is outside the cache. But what we are doing is we're trying to sort of relax this problem in some sense so that we can make some sense of this problem. Okay, so to tackle this earlier online set cover problem, I'm going to relax the definition in this fractional sense. So this is also called fractional relaxation, and I'm going to look at this relaxed version. Okay, fine. Okay, so all right. So let's write down this in a more sort of formal notation. So what we are saying is that if XS denotes the fraction to which you are picking a set S, then what you want is, okay, so what does a solution mean here? A solution here means that if you look at any element E, okay, and you look at all these excess values for all the elements which contain this element E. Okay, so these things should add up to at least 1. Okay, so earlier, if excess were only 0 or 1, this was the earlier definition of set cover. If that were the only definition, then this is a trivial thing. It's saying that for every element you must pick at least 1 set covering it. But now we are saying that for let's say there are 3 sets containing this element, and I could be picking these to a fractional extent. So I could be picking this to a 1/3, this to be half, right, and maybe this one to something else, right? Maybe another 1/3. So that if you look at their sum, it should exceed 1. Okay. Okay. So all these excess values should be between 0 and 1. So this is called. And what do you want to minimize? And again, if you're picking a set to a fraction of only half, I will only count that as picking half. So if you pick a set to a 1/3, I will only count that as a 1/3. So this is your objective function. If you want to minimize, so it's just saying that you minimize instead of saying minimize the number of sets you're picking, you minimize the total fraction of the sets you're picking. And if you're in the weighted set cover setting, then if sets have weight, then you can again generalize it by saying that you want to minimize. So if a set has weight 10 and you're picking half of the set, then you're going to pay 5 for that. So again, natural manner. So all of this is just saying that if my sets were somehow fluid and not in terms of like, I don't have a 0, 1 kind of thing, but if I could pick a fraction of a set, then this is the fractional version of this problem. Okay. And now again, I can talk about online fractional set cover. What is online fractional set cover? Online fractional set cover is where you have these variables xs. So initially think of all these variables are 0, that is you have not picked any set. And over time, you can start picking these sets, okay, fractionally. So what you could do is you can start with xs being 0 and slowly increase these over time. Okay, so these can only monotonically increase over time, they can never decrease. Okay, so for example, suppose at this time you have not picked this set. At a later point of time, you pick it to an extent of 0.1. Then maybe at a later point of time, you can pick it to a 0.3, 0.5, and so on, all the way to 1 if needed. So this is how each of these variables can evolve. Okay, so this is the meaning of online fractional set cover. So online is just capturing the fact that over time these values cannot decrease, which is just saying that earlier if xs were only 0 or 1, it meant that once you pick a set, you can't discard it. But now we are saying that these values can only increase over time. Questions? Okay, good. So now 2 questions arise. One question is, what's the, okay, so fine. So how do you now solve online fractional set cover? Okay, so, or, how do you solve weighted version, or how do you solve the multi-cover version? Okay. And the second question is, what happened to my actual set cover problem? Because this is not what I wanted to solve. I wanted to solve the set cover problem. Okay. And, there's also this notion of what is called integrality gap. Okay, integrality gap essentially says that for a problem, the optimal set cover problem, okay, and the optimal fractional set cover problem could be different, right? So for example, it can happen that if I give you a set cover problem, you need 10 sets to cover everything. But if you're allowed to fractionally pick sets, you may be able to do with just 6. Okay, so so just because you can do well with respect to fractional set cover does not mean that you can do well with respect to the actual set cover problem, because there is a gap here, right? Maybe you can do very well with respect to fractional set cover, but it does not imply that you will get the same guarantees for the optimal set cover, because there is a gap between the optimal solutions for the 2 problems. Okay, so this is called integrality gap. That is, whether you look at the integral version or the fractional version, if there is an inherent gap between the 2 problems, then you will incur that factor in your competitive ratio. Okay, so for example, for the set cover problem, this gap is log of the number of elements. So there is nothing you can do. Sorry, log of number of elements, number of sets, right? Log of the number of sets. So m is the number of sets. So you will have to incur this much. I keep messing this up. This should be log of number of elements. You will incur this much loss in your comparative ratio, just simply because you're going via the fractional route. However, if you look at the paging problem, okay, if you look at the weighted paging problem, it turns out for those kind of set cover instances, the gap is only a constant. Okay, so if you look at the optimal set cover instance and the optimal fractional set cover instance for the kind of instances we are constructing, these are very special kind of set cover instances, because the sets correspond to intervals. So these are very special kind of sets, and for these kind of sets, the gap between optimum fractional and integral, in fact, is 1, so it's not there. So you don't lose a factor log n, at least in the integrality gap sense. But of course, you still have to figure out, if I give you a solution for the online version, how do you get a solution for the actual integral version? Okay, so let me just summarize where we are. We are at online fractional set cover. And from there, I want to go to online integral set cover, actual set cover. And if I can do that, then I can also solve online paging, because online paging, as we saw, can be framed as an online set cover, or actually should be a multi-cover. Okay. And this kind of route is template holds for weighted set cover, for generalized caching, for elastic caching that I talked about last time. For the time window case, you have to be more careful. Again, one goes through a set cover problem, but the connection between set cover and online paging is more subtle, okay, in that problem. But essentially, this is the template one follows for a lot of these paging problems. Okay, and in general, I want to say that in any online problem, this is a template that people have been following. If you know what K-server is, if you know what load balancing is, that you first look at the fractional version of the problem, try to solve the online fractional version of the problem, and somehow try to get to the integral version from there. Okay. Now, both of these are non-trivial steps. Okay. How do you get a online solution for the fractional version? And even if you have an online version for the solution of the fractional version, how do you go to the online solution for the set cover? Both of these steps are non-trivial. I don't think I have time to do all of this, but what I will do is I'll show you how to do online fractional set cover, at least the basic version.
One question.
Yeah.
So you mentioned this in you're using the property that the integrality gap is constant for the particular set system.
Yeah.
So is it because of the? I mean, there's some set system has VC dimension low, let's say the constant VC dimension. Is it not those kind of set system? It is this integrality gap is small or something, or? So
no. So for a constant VC dimension, for all we know is these guarantees which tell you log opt times log opt. So I don't think you directly get constant just because of constant VC dimension.
Okay, Broniman Goodrich kind of technique.
Yeah, that will give you opt log opt. But here it's even very simple. It's like these sets are like intervals, right?
Okay.
And so you use the property that this is some sort of interval graph kind of thing.
Okay.
So just because they come from these intervals, you can use various kind of techniques here to prove that. I mean, you can yeah, I mean, you can even prove that integrality gap is 1 here, for example.
Okay. Yeah, because I mean, offline case it's polynomial time solvable, so it's
yeah. So offline, is a totally unimodular. So you can use various techniques of proving that this is integrality gap is 1 here. Okay. So right, yeah. And if you're talking about generalized caching, then it's no longer the integrality gap is not 1. In fact, it is unbounded if you write it like this. But you have to add more inequalities, which are called they're called knapsack cover inequalities. If you write knapsack cover inequalities, then you can show that the integrality gap becomes a constant. So you need to sort of enrich this relaxation if you're talking about generalized caching.
But generalized caching, you need some assumption, because you mentioned knapsack is a special case, and for knapsack you have unbounded competitive ratio. So
the knapsack, why do we have unbounded competitive ratio?
So for online knapsack, you have unbounded competitive ratio.
Oh yeah, but this again not Online knapsack. What is online knapsack? Where? Oh no, but in online knapsack, the pages, the items are coming one by one, right? But here the set of pages are given to you. It's the covering constraint which is coming over time.
Okay.
So it's a slightly different connection. Yeah.
Thanks.
Yeah, but you still have to write a different LP relaxation. This LP relaxation, if you just say that, what will, for generalized caching, if you just say that if you look at every set S, and if you look at the size of this set S, and this has to be at least some B prime. If you just say like this, it has an unbounded gap. So you want to write what are called the knapsack cover inequalities. You want to enrich this, and then the integrality gap comes down. Yeah. All right. So maybe in the next 5-6 minutes, I will just go over this fractional set cover and tell you about it. But what I want to tell you that this is the general template, which is very useful in all of these problems. Okay. Okay, so let's look at the basic set cover problem that you want to minimize the total sum of excess values. And the condition is that if you look at any element E, right, then the sum over all the sets S such that E is in S, excess has to be at least 1. Okay. Okay. And what I do is, okay, and let's have some notation. Let's say N is the number of elements, and M is the number of sets. Okay. So initially what I will do is I will set all the values XS to 1 over M. Okay, M is the number of sets. So if you do that, then this objective function is only 1. So you're paying 1 unit only. That's okay. That's a small amount. Now for our okay, so far so good. Okay. Now when element comes, right? Let's say an element arrives. And think of this M as okay. So when an element arrives, you look at all the sets which contain this element. Okay, and if this condition is satisfied for this element, then great, you already have enough sets to cover this element. Okay, so suppose this condition star for the element is not satisfied, otherwise there's nothing to do. Okay, so let's say at time t, some element ET arrives, right? Okay, and suppose star is not satisfied for ET. Okay, so that is summation S where ET is in S, XS, suppose it is strictly less than 1. Okay, so what you do is you double all the excess values. Okay, not all the excess values, but only those sets which containing E, right? For those sets S which contain E. Okay, so far so good. And now if this condition is satisfied, great. If not, then you again double them. Okay, so you repeat this step. Okay, so you just repeat till this condition is satisfied. Okay, and that's it. Okay. So that's the complete algorithm. So note that is this algorithm clear? Okay. Now to analyze this algorithm, one way would be to go through the dual, which works if you have more general version of set cover. But for just this version, I can give you very simple proof that this is. So I want to prove that. Okay, so the claim is that this is big O of log n competitive. Okay. That is remember what's the meaning of the statement. The meaning of the statement is that if you look at the value of a solution, this solution here, summation S XS, then this is at most log m times times the number of times the optimum solution value. Okay, and the way to think of this is the following. Okay, so whenever you double, what's the increase in the objective function? Whenever you double all these excess values, note that these excess values were adding to at most 1. So if you double them, you are going to add only 1 unit to your objective function, right? So the first observation is that when we double, we increase the objective function value by at most 1. Why? Because let's say these summation x's were adding to some value. When you double, that's exactly the increase in your objective function, right? So if you look at the summation xss, this number, this quantity increases exactly by this amount, and so it is at most 1. Okay, and so we have to somehow figure out how to charge this, right? You want to charge this to somebody. You want to account for this increase to somebody. Okay, and let's say that the optimum solution has some sets. Okay, so let's say the optimum solution has sets S1, S2 up to Sk. All right, then there must be one of these sets which contain this element Et in the optimum solution. So this is the optimum solution. Okay, let not use K, let's say Sr here. So suppose the element Si contains Et. Okay, so I charge 1 unit to Si. Okay, so I charge 1 unit to Si. I say that I will I will charge this money that is is incurred to Si. Okay, and the point is that how many times which will a set Si get charged, right? So how many times will we charge Si, right? Well, if you think about it, right, Si is present in the sum here, right? In this coefficient here, Si is present as well. And so each time you charge Si, the value of xSi doubles, right? So each time we charge, the value of xSi doubles every time we charge it, right? Right? Doubles whenever we charge it. Okay, and it can only double, and of course, when xSi crosses 1, then this condition will always be satisfied. So when xSi crosses 1, you will never charge Si again, right? So you start with 1 over m, you go all the way to 1, and at this moment, and each time you are doubling, so the number of charges that you will do to Si will be at most log of m. Okay, so that's why you get log m competitive. Okay, so far so good.
So where does it fail for general set cover? I mean, where do you use property of your set system exactly?
Where do I use property of what?
So I mean, this log m, is it true for general set cover as well, not only for?
Yeah, this is true for general set cover, right? And if you look at what m is for us, right? What is m for us? M is the total number of sets. And in my reduction, right, the number of sets were huge, right? The number of sets are like for every page, it's like t, right? The number of time steps. So this says that you only get a log of t where m is the time step. But what you can do is, and I'll just leave it as an exercise, you can get a log of okay, I need to invent a new number now. Let's say you can get a log of b competitive algorithm, where suppose each constraint on the left hand side has only b variables. Okay, so then you can get a log of b competitive algorithm. Okay, so what you can think about it, how to do that. You can instead of initializing as 1 over m, you can initialize these as 1 over b. So and you get a log of b competitive algorithm. Now if you look at the set cover connection with paging, the parameter b is at any point of time you only have n pages. Okay, so it doesn't, this parameter m doesn't become like t, it becomes like stays like n. And if you talk about the set multi-cover problem, almost the same reduction works, and you can show that you can make that n equal to, replace that n by k also. Okay, so all those things I will not show you, but because I'm out of time, let me say
weighted version, will it also work? The weighted set cover?
Yeah, let me just talk a little bit about, there was some other question. Sorry, I'm not able to see your faces. Was there another question here?
No, I was actually going to ask you this, that if I had not set the initial value to be 1 by m, but a smaller value, then in fewer log of that many steps, we would
yes. So if you start with delta here, then you will get like log of 1 over 10.
Yeah. So my question is, the fact that the algorithm knows the value m, that's a big thing, right? That because I'm giving the input instance in sequential fashion, right? So m itself be something that the online algorithm, the adversary can control?
Well, at least for the problem that we are talking about, M is not known. But as I said, if the left-hand side has only B variables in it, then I can start with excess as 1 over B for these guys. Okay, so that's why in actual any particular even if you don't know M, you can get around it by just looking at each constraint and seeing that how many variables are there on the left hand side. So although I didn't say this, yeah, that's a good question, but you can get around this issue. Yeah.
Right. Thank you.
Yeah. Good. For weighted, yeah, the question was what happens in the weighted set cover. Good. So okay, so let me quickly say that. Maybe it'll take me 2 minutes to say that. So let's say you were minimizing. There were weights also here. Okay. Now, the one idea would be to again, why did I choose 1 over M? The reason why I chose 1 over M was because if you add up all these excess values, initially it is only 1. So you don't that's a small price to pay. Okay. And let's say all these WS values are at least 1. They're integers. They're more than 1. Doesn't matter. Just a scaling issue. So what would be the initial values that you will give excess? Okay. So the initial value you can give them is, let's say, 1 over M times WS. Let's say I do that. Okay. So again, your total initial value will be 1, which is good. Okay. And again, suppose you don't satisfy this constraint. How would I update my excess values? Okay, so now one idea would be to just mimic the whole thing, that you update your excess value by multiplying it by 1 over WS. Okay, so sets which are very expensive, they are updated very slowly. Sets which are more expensive, they're updated in a faster manner. And the reason why I do it is, if you look at this, what is your increase in the objective function? Increase in the objective function would be exactly 1 here, at most 1 again. Why? Because it is the increase in excess value is excess over WS times WS. So this WS cancels out, and you can get the same guarantee. Okay. So far so good. Now the question is, how many times will you charge a set S? Okay. So now you're increasing in steps of 1 plus 1 over WS. So it will be log to the base of 1 plus 1 by WS, right, of M times WS. Right. This is the number of times you will charge it. And this is same as, roughly, if WS, think of it as a large number, this is log of MWS by log of 1 plus 1 WS, which is WS times log of MWS. Okay, fine. So, and I could have charged a set about WS times, because WS is what optimum pays for this set. But instead of getting a log M approximation, I get log of M times WS. Okay, which is not good. I really wanted a log M approximation. And you can think about it, and the way to fix it would be that, instead of doing multiplicative update in the beginning, you want to do some sort of additive update. Okay, so if I add, instead of just doing a multiplicative update, think of 2 phases in which excess is increased. Initially, I increase it starting from 1 over MWS, and each time I'll just keep on adding 1 over MWS to it. I won't do any multiplicative update till I reach something like 1 over WS. And then I do this multiplicative update. Okay, so essentially the same kind of ideas work, but you need to be slightly more careful with the multiplicative update here. Okay, you need a slightly different expression, just so that you don't get this log of MWS. You get only a log M. Okay, but you can read all that. I can give you references. But only this is a small technical change. But essentially the same kind of ideas will work for multi-cover. It will work for weighted cover. It can even work all the way up to generalized set cover, provided you use the right kind of inequalities for it. Okay, I guess I'm out of time, so I'll stop here. I just wanted to say that for all the extensions that I talked about, very simple templates work. Very simple ideas, very similar ideas work. But you have to be more careful about how do you solve the online version. How do you convert from the online? I didn't even talk about how do you go from online version to the actual version, fractional version to the actual version, right? How do you actually get to actual set cover problem? Okay, there's also in the usual set cover problem, you will just do what is called randomized rounding, and you lose another logarithmic factor. But in paging, you can do some more subtle things. You can do more clever things. and that's where you only lose a constant in the competitive ratio there. But these are non-trivial ideas here. I don't have time to go over them, but I'll stop here. Okay. Any questions?
This non-trivial idea, does it use integrality gap or a property of LP, or?
No. So what it does is what you have to do is, if you have a fractional solution, what you want to do is, suppose you have some fractional solution. Okay, so let's say you have 4 pages, and suppose you had half, all of them were half. Okay, let's say for the time being. Okay, now what you will do is you will maintain some sort of distribution over these pages. So for example, I can say that suppose your cache size is 2. Okay, so you will say that I will have a cache which contains AB, and this cache I will think of keeping this state in my cache with probability half, and I will keep CD with probability half. Okay, so you sort of maintain some sort of distribution over these caches, so that if you add them up, these are like the marginals that you get. Okay, so the excess values are just telling you the marginals, and you sort of evolve these distributions. Okay, and for you kind of say that you have some sort of trajectory here. At each time step, you will have one distribution, and you will have some sort of trajectory, several trajectories. Each of these trajectories will be containing a valid cache states and evolving those cache states, and somehow the average has to be this fractional solution. Okay, and then you randomly pick. So this, see, in the solution for the fractional set cover, I never used randomness. So the randomness is only coming in this translation from online fractional to online actual set cover, even in the case of paging. Okay, that's where the randomization comes in. Okay, so basically what you do is you maintain this probability distribution, and you say that I'll pick one of these trajectories at uniformly at random, and just go through that trajectory. Okay, roughly that's how this is done.
Okay,
I
think Amantak has a question. Yeah. Go ahead.
So Amit, you said that so this is the way you described, you get a log m, right, for the fractional packing thing.
Covering problem.
For the covering version, yes.
Yeah.
So now then you said something that you can get it down to log b.
Yeah.
Is it log b or is it b? Because isn't b like the frequency of the element?
No. B is not the frequency. Frequency would be the opposite. Like this is like the row, number of entries in the row. Frequency is like the number of entries in the column.
Oh, I see. Oh, I see. This is the left side of these constraints.
Yeah.
I see. Okay.
Another question. So, sorry, please go ahead.
Yeah.
Go ahead, Arindam, please.
Yeah. So for this problem, there is hardness. Like I think Alon had some hardness of log n or something.
Yeah.
But those are for deterministic algorithms. For randomized algorithms, is there any hardness?
No. Yeah. Even for randomized, almost log n is almost log n. Okay. There's some log n over some log factors, but yeah, even for randomized, these gaps are known.
Okay. Thanks.
So one question, Amit.
Yeah.
Right now, would you think are, say, 1 or 2 interesting open questions regarding online set cover or online caching?
Right. So online caching, as I said, like there are many settings which are unexplored. So let me just say online caching, because set cover, I believe, of course there are other. Okay, so maybe because we're talking about online caching, so there are several. I mean, first of all, what would be like people haven't considered these in the sort of the many versions in the sort of Markov model, right? Where you say that there is some locality of reference, and what can we say about weighted paging? Can I do better, or can I get some guarantees for weighted paging there? The other would be I don't know any sort of rent or buy kind of models. So, for example, I talked about elastic caching, where for each time t, your cache size can change, and if you maintain a cache size s t at time t, you pay some cost s of t, right? So in your objective function, of course, you have the usual set cover thing that the number of sets you have picked, plus for every time t, you pay some cost of maintaining size st. Okay, but this is not how generally it is done. The way it happens in practice is that if you go to, for example, Microsoft or Amazon, what's that called, the platform which allows you to rent. Okay, Microsoft. I think for Microsoft it is called Azure, and for Amazon I forget what it is called. But what it says is that right. For Amazon or for these caches, you can rent them for varying amount of time. Okay, so for example, I can say that I want 2 MB cache for 10 days, and it will cost me so much. Or I can say I want 10 MB cache for 5 days, and it will cost me so. So this is really how they define elastic caching, and we don't know any comparative algorithms here. So it will be good to extend the ideas that I mentioned earlier. And then I did talk about delay models, where you don't have to satisfy the request right away, but you can satisfy it at a later point of time. But again, we don't know how to handle generalized caching in this delay model. We can only do sort of weighted paging here. So that's another open problem one can think of. I think all of these are interesting directions. Yeah, sorry.
In this delay model, if the amount of delay is prefixed, the adversary can repeat the same page multiple times, literally that amount of delay time, and I learn nothing more, right? I'm allowed to make a decision a certain pre-specified period of time later, right? In that, if adversary basically reveals me nothing more, like it keeps on repeating the same requests that are already in the cache, am I really gaining any advantage by having this delayed sort of this window?
No, so it's not meant to help. If you thought this would be an easier problem, it is not an easier problem, because what I can do is that, I can think of the delay model, the original problems as a special case of this, because suppose I say that the delay is 0, right? You have to submit it right now. I can always say that the delay allowed is 0. In which case it's back to the original problem.
Yes.
Right. So in terms of it's a more difficult problem, because I can give different amount of delays for different requests. So I mean, the way it is useful in practice is because if there are 2 requests for a page and those intervals are overlapping, then you don't have to bring it twice in the cache. You can just bring it once in the cache. But how to solve this problem, it's a more difficult problem, right? So solving it is more difficult, but in practice using it helps.
Right. So that's what I was thinking. It seems like a bit of a resource augment, like just a little bit of advantage for the algorithm, in the sense that it gives this, you don't have to make immediate decisions at this moment.
Absolutely. That's how it helps you in practice, right?
Beyond this sequence, maybe are going forward. And it probably definitely helps when you have locality of some correlation, right? When adversary cannot behave in an absolutely pathological fashion. So I was just thinking that we do have the adversarial model. How much benefit can delay really give? But yeah, general problem.
Yeah, you're right. You're absolutely right. And then all of this are I didn't talk about K-server. K-server is a more general version of this problem, and you can ask all of these questions in the K-server setting. And that's where it gets very interesting. We know very little about K-server actually. So for example, if you talk about the weighted version of K-server, we know very little about it. So there are many open questions if you go from paging to K-server and so on. All of these questions can be asked in the K-server setting also.
I see. Okay. Any other question?
So are there any resources online, you giving lectures or other things where people can follow up on this particular, how to use?
Yeah, sure. I can I can send you the references, and maybe he can share with everyone.
Sure. Thank you.
Yeah, so what about online set cover open problems, or it's more or less settled?
Yeah, so online set cover.
So the general case is settled as far as I know. There's a upper bound and there's like a sort of a very small gap of log n with the lower bound, but yeah.
Right, more or less it is tight, yeah. And I believe for weighted, yeah. So I mean, there are these recourse models, but I think they're also now somewhat well understood. I don't know. Are there problems in online set cover? I can't. Yeah, I can't think of any immediate questions. But again, there's a lot of work in online set cover. You should look at some recent papers. I can definitely send some recent works on online set cover. I don't know what are the remaining open problems here. So, for example, there's this whole model of there's of course dynamic set cover, where dynamic set cover says that you can change your solution at each time, then build a new solution at each time, but you want to minimize the time spent at each time a new element arrives. You don't want to spend too much time in modifying your solution. So there's a restriction on how much time you spend in modifying your solution. There's something called online set cover with recourse. Online set cover with recourse says that you again are maintaining a solution, but each time a new request arrives, you can change your solution, but you can't change your solution too much. Okay, maybe you can take in 5 sets, throw out 5 sets, but that's all you're allowed. Okay, so there are models like these, and in each of these models there are some specific open problems. You can look at the papers. So there is a very rich class of models here, and I believe if you look at each of those papers, you will find some specific open problems.
Thanks.
Yes, sir. So in the delay version of the caching problem, can we put a cost on the amount of time after which the request is served?
Right. So you in our paper we also do that. So basically, instead of saying a hard deadline, that is, service a request, this request between current time and current time plus 10, we can say that you can request it, service it at any point of time, but as you delay things, you will pay more and more penalty. So there is some sort of penalty model where you say that you can service it at any point of time, but the longer you delay, the more cost you will incur because of this delay. Yeah, so you can have models like that.
So then,
and if you look at our paper, we also do this delay models.
And then in that case, what will be the objective function that minimizing
objective function is again the total first of all, the weight of the pages which are evicted, that's one component, and then plus the total cost of delaying things. Okay, and there could be some relative weightage between the two, right? Okay, so total eviction cost, weighted eviction cost, plus let's say some alpha times the total delay penalty.
Okay, thank you.
Okay, any other question? Okay, so then thanks Amit for the great talk.